Hi there, I'm Roberto, and this is...
And I'm Will Chan. Yeah, so today we're going to cover some basic topics. We're going to cover why we're doing Speedy, what is Speedy, how does Speedy make things faster, what's the current status of Speedy, and also where we're going with Speedy. There's a lot of future work, but there are a lot of things we're doing right now and a lot of things we have planned far down the line.
Alrighty, so first thing we'll talk about is, what a web page looked like around May 2010. We'd already done some work on Speedy by then, but this is still basically informative. It's actually gotten worse than this in many ways. So the average web page has a whole bunch of resources, contacts a whole bunch of hosts. It is in the hundreds of kilobytes, and it is nowhere near as compressed as it should be. So when we looked at this, we realized that, as it says here, the incremental improvements to HTTP didn't really change things a whole lot. And we'd actually tried to make some changes as Google. We'd tried a different compression technology, and what we found was that ended up being rejected, at least temporarily, by our clients and actually by the internet simply because it didn't work. And the reason it didn't work, despite the fact that both the client and the server supported it, was that there were transparent proxies out there on the internet, and these transparent proxies would muck with the headers, or they would muck with the data, and they would make this communications impossible. So as an example there, the stripped accept encoding headers made it so that we couldn't actually advertise properly what compression protocol from the server to the client that we were speaking. Connection use in 2010 is shown here on this graph. So we see that things got worse since the previous thing. So there's a trend towards using more connections. Well, sometimes it's for good reasons. For instance, you want to split off user-developed and user-generated content from content which you believe should be secure, because it's difficult to secure user-generated content. But for the most part, this seems to be done so that you shard your domains and you allow increased parallelism, which is, of course, one of the big problems with HTTP, which is that it's head-of-line blocking, and you essentially only get, unless you've turned pipelining on, which most haven't, one request per connection at a time. That generally doesn't work so well. So
HTTP had all these problems, and we were thinking, since one of Google's major initiatives is to make the web faster, we wanted to rethink it, see what we could do to make things faster. Our goals are to make sure that we can deploy Speedy without requiring web content owners to radically change their websites. Obviously, we want to make the web faster, and this shouldn't require people to drastically rethink how they deploy their websites. It should be a drop-in replacement, and it should make things faster. So that's what we're going for. So basically, Speedy is not really that complicated. We see problems like headline blocking, concurrency issues with regards to only 6 or however many connections per host. So basically, we decided to deploy some basic features. Use a single connection, stop sharding across multiple host names in order to get more parallelism. Just use multiplexing instead. Add requests, a stream prioritization, so you can tag which requests are more important for the server to respond to. So basically, you should just have the client send the request to the server as soon as possible, and the server will decide when to send the responses in whatever order it thinks makes sense. So another area that we've seen incredible redundancy is headers. So basically, on every single HTTP request, you're sending, for the most part, the same header over and over again. VC, can you please mute your mic? So we made header compression mandatory. This results in big benefits, especially on the uplink. So Yeah, that was awesome. Another big feature is supporting server push. This is a fairly advanced feature and it has pros and cons, but we hope to see large benefits from server push. So yeah, it's not really rocket science. It's pretty basic, but we hope that it'll, show. And we have data that shows that it does increase the speed of web pages. So yeah, what is SPDY? SPDY is an application layer protocol. It's built on top. The current way that it's deployed is on top of SSL, TCP, and IP. So it's at the highest layer of the stack. We use mandatory header compression to reduce the redundancy in our HTTP headers. I guess all the stuff I covered in the previous slide. One important thing is that we are deploying over SSL. We think this is really important for the web. It's really lame that when you're in an internet cafe that anyone can just sniff your cookies. We think that everything should be secure. So that's one of the major reasons that we're deploying over SSL. Yes, and another major feature is server push. This should obviate the need for techniques such as inlining with data URIs. Yeah.
So the data that we see here are from lab tests that we did some time ago, but unless we say lab results, we believe these are generally still true. So we saw a significant reduction in upload bytes from SPDY, and this is basically due to the compression of headers that we were just mentioning before. So compression of headers, you may think, oh, it's mainly the cookie. Well, the truth of the matter is it's not just the cookie. There's a whole lot of data, actually, there's a whole lot of text that's there that happens every time, for instance, your browser saying what user agent it is. That string is actually pretty darn long. And generally your browser isn't changing with the connection. Every connection is going to be using the same browser almost all the time. At least if you're guaranteed that the connection is from client to server, which in this case we can guarantee. Hey, VC, please remember to mute. Hey, you in the conference room, that means you. Mute, please. All right. So download, as we can see, there was nowhere near as much impact here, and that is because the majority of the download is actually, unsurprisingly, what you want to see. It is data. So we are not reducing by a whole lot the amount of data that is downloaded, at least not today. And we're not reducing it too much today because much of the data, at least in our tests, was compressed. Now, as we mentioned in the previous slide, that isn't always the case. There are cases where we can't do that. There are transparent proxies that mess with it. There are transparent proxies that disallow us from trying to deploy new protocols, new compression techniques. Those shouldn't be a problem with SPDY, although SPDY itself won't lend a whole lot to decreasing the amount of your download. All right, the story with total packets. You'll notice that the reduction in total packets is significantly more than the reduction in the payload size. There's a couple reasons for this. The first one is, well, the payload size is actually a little bit smaller, so that has some effect. But there's another big reason, which is that if you're multiplexing over 44 connections, you're much less likely to have full packets, right? If you put it all over one connection, you can almost guarantee that every packet's going to be a full packet except for the last one of any particular non-idle session. So in that case, you're simply going to reduce by quite a bit the number of packets. And as many TCP implementations look at their congestion window in packets, this can have a surprisingly positive effect. Increasing parallelism, hopefully this will be obvious given the given the fact that SPDY does multiplexing and it doesn't have to have a new connection for each thing. So you can look at the slides if you want to examine this in more detail in the future. So multiplexing, and how does it compare to pipelining? Well, on pipelining side, it exists. It's been part of the specification since the specification was a specification. However, it was actually really hard to implement. And one of the reasons it's really hard to implement is just as we've had with compression, there are these transparent proxies out there that mess with what you can do. And it's kind of hard to detect them because of the word transparent. Sure.
And so I've had experience with this in the Chrome browser side. Another problem with pipelining is that it's really hard to detect when it's broken. What is a clear signal that HTTP pipelining isn't working? You get these weird errors, and it's hard to tell that the result of the HTTP or connection errors that you're seeing is because of pipelining. And that's because of all these transparent proxies who muck with it and do whatever they're doing. And it makes it really hard to see whether or not you can enable pipelining for this origin server or that origin server. And also, when you move to a new network and you have new intermediaries in between, then it fails again. So.
And then, of course, there's one other humongous problem, which is future-looking for pipelining, which is that thou shalt not pipeline for non-idempotent requests. And if you've been following what people have been doing with web pages, i.e. AJAX and increase in amount of interactivity, a lot more of what the web is doing is done over a put or a post, i.e. non-idempotent requests. So those can't be pipelined. So on the speedy side, we don't have to worry about, do we detect properly the fact that this is broken? It's not. We're guaranteed that given our deployment strategy, which we'll talk about more. We are guaranteed that we can do however much multiplexing that we want. Well, okay, I mean, yeah, we're limited to 4 billion simultaneous sessions, but I think that should be enough for anybody at the moment. And if it's not, we can put a new opcode and a new frame out there and change it. We can do better compression. As we mentioned before, server push. And of course, really important one, there is no head of line blocking. We can interleave data frames that we send back for multiple requests simultaneously based on their priority, and nothing gets blocked that shouldn't be blocked.
One other thing to go with an advantage of speedy over pipelining is that when the connection dies and your pipeline is 2, 3, 5, however many requests deep, you don't know how many of those were actually handled by the server. Whereas for Speedy, when the connection closes, it sends a go away frame which says I processed up to like this many SYN streams. So even if it dies in the middle, you generally have a better failure mode.
Yay, less ambiguity.
Yeah, so basically what this graph is telling you is that RTT is important. We've seen big increases in bandwidth capabilities, but the speed of light is not getting any faster, and RTT matters. So even though we have more bandwidth available, the actual usable bandwidth by web pages is not improving. So yes, round trip times matter. Basically, more data to show that RTT matters.
So in particular, in the previous slide, note that we have a log relationship with an increase in size, basically. Sorry, with an increase in the size of the pipe, right? So it looks like we're approaching some limit as the bandwidth increases. Of course, when you look at RTT, this is a completely different function. It's a line. And of course, linear relationships are far more powerful than logarithmic relationships, at least when we're trying to use it in this fashion. So, you know, the intent of these slides is to ensure that we know that a reduction in RTT matters a lot more than an increase in bandwidth.
So when we were doing Speedy, we were talking about where should we make the changes? Should we make the changes in the transport layer? Should we do it at the application layer? We know that there are problems in the transport. Like currently in transport, we have tons of separate connections. They don't have shared state, shared congestion control state, shared all the other connection state. you're not allowed to send data out with your TCP SYN. Actually, you are, but it doesn't really work on the internet yet. There are lots of problems with it. There's slow start. There's delayed ACKs. Like, these are all problems for. These are all things that cause latency for web pages. But the problems in the application layer are way worse. The connections are single threaded. You can only use one request per connection unless you have pipelining, but we've already talked about pipelining. There's tons of redundancy across requests due to HTTP request headers. And there's no compression going on there. There's not enough compression going on even in the response bodies. Basically, the benefits that we could get in the application layer are so huge, and it's pretty difficult to make changes in the transport layer. So we're going for the low-hanging fruit first. We need to solve the application layer, and that's what SPDY does today. So when we're talking about how to actually deploy SPDY, yes, we could try and change the lower level transport. As discussed, that's pretty hard. You would have to deploy kernel changes or build on top of UDP and then re-implement lots of the congestion control algorithms that is already given to you in TCP. And yes, there are problems with NATs. So trying to deploy over another protocol that's not TCP is fairly difficult. Yeah, so back to UDP, back to TCP. For most of the web, most of the internet, there are only really two ports that you have available. There's port 80 and port 443. Firewalls often will block all other ports. Lots of people debate this. We have data to show how successful this is. So port 80. Everyone always asks us, why aren't you going over port 80? Why aren't you using the HTTP upgrade mechanism? Yes, so the upgrade header, that would require a round trip. Like on top of the TCP handshake, you would have to do an HTTP upgrade in order to negotiate to another protocol. So that was not too good. We weren't very pleased by that. So luckily, while we're talking about our deployment strategy, the WebSocket team was trying to test out how best to deploy WebSockets. And they ran this experiment within Chrome where they tried to connect to port 80, port 61985, and port 443 and speak WebSockets. And as you can see here, the success rates are pretty horrible for port 80. It gets better for port 61985, but really, if you're actually trying to deploy it widely on the internet, port 443 is the clear answer.
And so to reiterate, right, why does port 80 fail? Well, it doesn't fail because the packets fail to get there. It fails because of these wonderful, horrible things called transparent proxies that were supposed to save us, but in actuality stifled any innovation because any innovation is not recognized and it basically fails. So this is what we found. Yes?
Question, why is HTTPS rate not 100%?
There was some. You mean HTTPS? There was some amount of failure that was common amongst all of them. So there were times when the browser was simply not able to connect to the internet, for instance, and we did not remove that from the results of the study. So the reasons that HTTP over port 80 and HTTP over port 61985 were different. It wasn't actually HTTP, but anyway, the reason over port 80 is because of transparent proxies, and the reason over 61985, we assume, is because the packets were never delivered. So that, in other words, we actually have less mucking about by firewalls over random ports than we have transparent proxies mucking with your content stream, which is a very interesting finding. So that informed the decision. What do we use? Well, we're going to use port 443 because we want some chance of getting this protocol out in our lifetime. Port 443 is so reliable, of course, because there are no transparent proxies mucking with it and because it does traverse firewalls. Perfect, right? So how do we actually allow us to upgrade? Well, we could have done HTTP upgrade, right? We could have done that equally over port 443. However, it would have introduced yet another round trip. And let me tell you, SSL already adds a round trip, which we will talk about in another slide. So we added an extension to SSL, which we are trying to push through any standards that we can at the moment, called Next Protocol Negotiation. And as far as I know, we have submitted patches for OpenSSL, which will hopefully make it into the next release, but we'll see. It's up to their maintainers. And NSS, of course, yes. So we're hoping that that will not just be for SPDY, that would be for upgrading to whatever protocol people decide to use on that port. But the nice thing about the port is, of course, to reiterate, nobody can mess with that data. That is excellent for the evolution of the internet because it means that we can continue to make new protocols. For instance, if somebody thinks up something better than SPDY, which hopefully will happen, they can deploy it.
And this is part of the SL handshake. So no.
Yeah. And it's part of the SSL handshake, so there's no additional round trip. So one of the questions that we've got a whole lot when we announced this decision to various people within the company when it was an experiment is, wow, geez, but isn't SSL so slow? Well, actually not so much. Our CPUs are a lot faster than they were when SSL originally got this reputation for being so slow. CPUs are significantly faster, and the implementations have improved a bit. TLS does increase bandwidth by a hair, but of course SPDY does header compression, and that ends up being a larger factor than the TLS overhead does. But yes, SSL does require some additional round trips in the beginning for the handshake. So you'll notice a thing that says, can we reduce to 0 RTs? Well, we can, and we did run an experiment, but the complexity of that implementation was such that we were not confident that it could be successfully deployed to the internet at large. So we're not going to propose that as a whole. But we will note that we hope that future work occurs in potentially revisiting SSL as well to allow for all of the innovations that we're doing with SSL today, but also to allow for a 0 RTT handshake. Because as you recall, RTT is the dominant factor in any web page load. All right, so here we see a diagram of multiplexing for SPDY. So we've tried to color things in different colors just to make it a little bit obvious. So we have a stream at a low priority of 3. We have another stream of a low priority of 3. And at some point in time, we have a stream with a higher priority, which would be 0. And what we see here is, first of all, that things are interleaved. But second of all, when we realize that there is more important data, we are free to insert it into the middle of whatever stream and thus delay delivery of the other streams. So that we can service that stream first. So what is SPDY? Here's what it looks like basically on the wire. Note that in reality these headers are compressed, as we've said multiple times. But basically if it was uncompressed, this is what it would look like. So this is a SYN frame. Its stream ID is 1. It doesn't have any associated stream, so it's not a reply to anything. Yeah. The priority is 1, which is a relatively high priority, although not the highest. It has 4 headers. It has these, and the headers are key value pairs, where the key is the first element and the value is the second. So the method, it was a post. URL is not something we use as a key these days, but basically, and I'll explain briefly why in a moment. User agent, etc., etc. Okay. So why is it not URL anymore? Well, we thought in the very beginning that URL would be a wonderful thing to have there because hopefully it's what people type into the browser line, into the box there. However, HTTP actually has some interesting redundancy here, which we found that we had to emulate in order to be compatible, or as compatible as possible. Basically, you can have a URL in the first line of your HTTP request while simultaneously having a different host header. Great. So we actually have to have two separate fields for this. So in modern Speedy implementations, as is indicated with the draft, if you go to the Speedy website, which we'll tell you how to find later, you will find that there's actually two different header fields there. So, does it work?
So initially, when we were working on Speedy, we wanted to see how it would work. So we ran a bunch of lab tests. You can read what we've done here. Basically, we tweaked all the major variables, packet loss, bandwidth, RTT, and we examined the top 25 web pages. This is just lab results. So later on, we'll present some real-world findings, but this is from the lab. Yeah, so with real-world packet loss set to 1%, Speedy. Oh, sorry. So the slide says flip. That was the internal code name for Speedy before we settled on Speedy. So whenever you see flip, we mean Speedy. So we did do some internal lab tests of Speedy not over SSL. So you can see that the results were pretty promising. It was very exciting. 41 to 47% faster for packet loss between 1 and 2%. Another big question is, what kind of websites is Speedy actually good for? Is it good for the top websites, which are theoretically highly optimized content? So here we randomly picked sites from the top Alexa, the top 1,000. Overall page load time speed up was 40%, which is pretty good. Sorry for the truncation on this graph at the bottom. That does not start from 0. It's from 1200, but as you can see that Speedy, not over SSL still, has huge improvements over HTTP.
And I'll want to note one thing about these lab results. They really didn't weight mobile very much. And with the advent of mobile, of course, RTTs unfortunately have gone up, which means that RTTs matter a whole lot more. So things that can take off one RTT don't show anywhere near as much improvement as you in these slides as you'd actually have in a study redone today.
And by things that would remove one RTT, Roberto means things like server push. Yeah, so Speedy does wonders for web page loads. Uses far fewer connections, which is awesome since you don't need to open up new TCP connections, do new DNS resolutions, have much more buffer overflow on the internet. Using fewer connections is awesome.
If you're not familiar with buffer bloat, please put it into your favorite search engine and look it up because we need to kill it.
Why don't you just cover it?
All right. So what is buffer bloat? Sorry. All right. Buffer bloat basically is that for various reasons we have increased the amount of buffering we have on intermediaries between you and the server and between the server and you. And note, for what various reasons, these may not always be the same path, but often are. So your cable modem, or at least cable modems very recently, would have a fairly sizable buffer in them of certainly a megabyte or more. And the interesting thing about that is, of course, it takes some time to drain a megabyte. Maybe you're one of the lucky few, and your upload speeds from your cable modem are significantly faster than a megabyte per second. But for a lot of people these days, it's still not true. And I'm just using this as an example, and this actually occurs in routing devices out in the internet as well, so it's not just limited to your endpoint. But the larger the buffer, the longer it takes to drain. That is the essential thing that people need to understand about buffer bloat. So you have this wonderful voice chat that you want to do. So you send some packets, and it goes into that packet queue on your cable modem, which takes 1 whole second to drain. That is buffer bloat. We don't want that. We want appropriately sized buffers so that we can get packets through with reasonable latency and with dependable latency, so that the amount of latency doesn't change all the time by any great factor. So the more connections you have, the more likely it is that you're going to cause some buffer bloat, because the amount of space that you're going to use in each of the buffers will actually be potentially more.
Not that we've spoken too much about buffer bloat already, but basically, my suspicion is routers out there just wanted to say that they had less packet loss. So, like, how do we prevent packet loss? Well, let's increase buffer size, and it just increases latency. Really, if there is congestion and the buffers are getting overloaded, you should just drop packets. That sends the signal back to the peers that, yes, there's congestion, you should back off. So real-world numbers for SPDY. This is Chrome 12. SPDY compared to HTTPS. We will have numbers, we will have an announcement versus HTTP later, but within Chrome, we have an experiment where we, in our NPN extension, we advertise SPDY for 95% of the cases, and for 5% of the cases, we do not advertise SPDY. So we just do vanilla HTTPS. And for sites that do support SPDY, we compare the page load time for SPDY versus HTTPS, and you can see that we have a 15.4% improvement out in the wild.
And one thing I'll point out about these numbers is, of course, in April 5, there weren't all that many external websites that were using SPDY. And unfortunately, that's still true, although it seems to be rapidly changing, which is very exciting. So this data is also colored a bit by the fact that, unfortunately, the major consumer of SPDY was Google. And Google has traditionally done a pretty good job of optimizing web pages. So the fact that we're seeing this much improvement for data which is dominated by Google is pretty interesting.
More qualifications on the number. If you look previously, many of the major web properties at Google that supported HTTPS, like most of the traffic would be stuff like Gmail or whatever, where page load time is not a well-defined, not a really good metric for actually whether or not you're speeding up the web page, the browsing experience. You have to use other metrics, so this should be taken with a grain of salt. But, well,
it's as good as any other metric. But it's as good as any other metric. All right. So here's the wonderful thing we wanted to say. So as hopefully many know, Google recently launched search over HTTPS. Well, it was really great to see that for the Ajax search, we were actually faster over SSL because we were using SPDY than HTTP, which was kind of a wow moment, you know, that this was, okay, maybe some of us expected it, but, you know, for the majority of people, this was a somewhat unexpected result. So we just want to say with this that, look, SSL can be faster than HTTP for your website, right? So you think it's going to add latency? It may not, at least not if you use SPDY.
And we will be presenting numbers. Well, someone from Google will be presenting numbers for this at the next Velocity conference. So stay tuned.
One question. The chart that you showed before, the Chrome chart, are these both limited to Google.com sites?
So these are aggregate statistics as measured by Chrome. Chrome does not record any information about which sites it went to. So we can't actually know that this is Google, but as far as we know from looking at our server numbers, the majority of this data should be coming from Google.com by weight of volume, basically.
Yes. So the speedy one I understand. The HTTPS one, is it like basically, is there some sort of experiment control set up in Chrome?
Yes. So Chrome randomly disables speedy today for 5% of its instantiations.
Okay.
And that's how testing.
Yeah, basically on startup, Chrome will use a random number generator, and in 95% of the cases, it'll activate speedy. In 5% of the cases, it will not.
Okay, so these are HTTPS responses for speedy capable servers, right? The second
Yeah.
bar
Correct.
on that. Got it. Thank you.
And so they are actually speedy capable, so it goes through NPN and ignores speedy, and it's not all HTTPS, right?
Correct. We are only comparing numbers for servers that use the NPN extension.
Alrighty, so yes. So the question was, will it be the case that on mobile that HTTPS using speedy is faster than HTTP? I would suspect it could be significantly faster on mobile for various reasons, but it does depend on what exact implementation we use. So again, the interesting thing about mobile is for many mobile technologies that are deployed today, the RTT is significantly higher than what you would have on your desktop. So anything where you can reduce the number of RTTs is significant. Now, Speedy reduces number of RTTs in a number of ways. The first one is multiplexing, right? The second one, which is a bit of a surprise, is that for mobile, since you are so bandwidth constrained, header compression ends up being a significant reduction in the amount of bytes you have to send, and thus allows the server to respond significantly faster. And then the thing that's on the timeline, although we haven't played around with it too much for lack of time, is server push. So we also know that there are things that we can do with Speedy that we really haven't turned on that we suspect, at least for mobile, can make another significant difference.
By the way, all these numbers we've presented previously are for websites that are not Speedy optimized. So they are not leveraging things like Speedy server push. They are not undoing hostname sharding. So basically, there are more gains to be had. This is a drop-in replacement. So we're Speedy is already improving things as is. We can save RTTs by undoing hostname sharding, so you don't have to do the extra DNS lookup, the extra TCP connections. And those are huge for mobile.
Right. Another interesting thing for mobile is that there are two things that seem to consume battery most on mobile phones, and they are display and radio. And the interesting thing is the fewer bytes you ship and the faster you get your web page, the faster you will get the radio turned off. And so you can actually see an increase in battery life, which is surprising. The CPU isn't the main consumer. It's these other battery drains that are the main consumer of battery. So anyway.
Live question?
So the question was, there was a question of two parts, really.
What follow-up the power?
Yes. One was talking about the fact that there's a significant cost to turning the radio back on. And so that was an observation. The other one is that another observation that there's significantly more packet loss over 3G than the 1 to 2% that we had here. So I can honestly say that we still don't really know. We don't have enough implementations out there in the wild that we can tell you what actually occurs. And and I think that we're going to require that before we get you any real conclusions. I can say that Speedy does have a mechanism in it which is interesting that allows you to not have to use TCP keep alive, which is the ping frame. So basically you can test for the connection for liveness using the Speedy protocol layer alone without having to actually call any handlers on any server. So this allows us to test that. It allows us to assume that a connection is open and thus have it open without having the cost of waking up the radio randomly for packets that have no utility whatsoever other than keeping the connection alive. So, all right, let's go.
Okay, so
May I
current
ask a question
speed.
here?
Sure, but we're running out of time, so yeah, go ahead.
Okay. Well, you mentioned that Speedy is enabled on Home and that we use Speedy for all the secure traffic at Google. However, when I'm using the Google services, I get HTTPS. Why is that?
What's the
Shouldn't
question?
it be Speedy? Well, when
So
I use
Speedy, Speedy, when you use HTTPS in Chrome and it talks to a Speedy capable server, it will negotiate Speedy. So Speedy is not a new scheme. So you will not see Speedy : / It's still HTTPS : / or HTTP.
Okay. I see. Thank you.
Okay.
If you want to find out whether or not you're actually speaking Speedy, we can talk to you later. There's some Chrome URLs that you can type in that will show you what sessions are speedy, etc. I imagine that Firefox has something similar, and so we'll find out from Firefox Dev what that kind of thing looks like when they've given us more information.
So yes, current deployment status of Speedy. Speedy has been on by default in Chrome since Chrome 6. And as we discussed previously, we are running a 5% holdback so we can gather numbers. It's on. So if you're using Chrome or another Speedy capable browser like Firefox 11, then it's on for all Google SSL traffic. We have a number of other Speedy implementations out there. We have an open source Speedy proxy. It can serve as a forward proxy or a reverse proxy. There's also out in the wild, Amazon has deployed the Kindle Fire, which uses Speedy proxy. Android browser has supported Speedy since Honeycomb. Firefox will support it in Firefox 11. We have ongoing work to support it in Apache. There actually is an existing mod Speedy. It sort of sucks because it doesn't do multiplexing. It's correct, but it's very suboptimal. We're going to fix that. There are a ton of other Speedy implementations out there. I get all these alerts that say, hey, someone has written a new C implementation of Speedy, or today I got an alert telling me that someone wrote a new Erlang implementation of Speedy. It's always very surprising and very interesting to hear about this. But yes, so basically Speedy works, is out there in the wild. You can use it to speak to Google. There are other servers out there. Strangeloop deploys it for certain websites. And yes, there are other ones which we're not allowed to talk about. External people will have to announce it themselves.
A quick question on Android. Would I get?
We hold any more questions to the end because we have enough. Yeah, we only have 5 minutes to go through the rest.
Should we just?
We'll skip this one.
Yeah.
All right, so one of the things we like to point out is CWind, which is the congestion window for TCP, which is how we do rate limiting for bytes sent on a TCP connection, is still a problem. There are various kernel changes that can be done, but of course, deploying kernel changes isn't exactly the easiest thing in the world, especially when the equivalent changes for Windows can take a very, very long time to go out there. Even on Linux, there are various problems. just talking about the TCP layer things as well and ignoring the implementations, the back off for a single connection versus many connections is, well, it's unfair, right? You end up, if you compare a speedy connection as it is today without any TCP modifications, which we may talk about later if we get time, it is likely to have a significant increase in bandwidth reduction as compared to the many HTTP connections if there is randomized packet loss. So we are actually talking with people to fix that. So what are the next steps?
But basically, there's an incentive for web apps to open more and more connections if they want to have more CWIND available. So, and that's not really what we want to incentivize people to do.
So what are we doing going forward? So our number one thing that we do right now is we're trying to help the community. So we have been working on updating our draft 3 spec. We are beginning work on a speedy compliance test suite, so hopefully that'll make it easier for external implementations to find out that they are indeed doing things wrong, or in hopefully other cases that they're not doing it right. We're going to split out the speedy HTTP gateway we talked about briefly before so that you don't have to have the whole Chromium code base to compile it. We've heard complaints that that's a bit of a barrier. And of course, as we mentioned before, we've been working on making Mod Speedy in Apache a real first-class citizen in the Speedy world. All right, so one of the things we'd really like to talk about, and one of the reasons I said no to questions before, what are Speedy best practices? These are the things we believe you should do if you want your web server to perform well for Speedy. So number one, it's really optional. You don't have to shard your domains. So if you were sharding your domains so you could get more concurrency in the past, you don't have to. Depending on how your cert structure is done, you may actually end up with multiple Speedy connections. If you don't shard them, you won't. And again, there's no concurrency problem with Speedy. Watch your cert size. So do some basic blocking and tackling for your SSL. Make sure that the cert chaining is done properly so that you don't have to add a whole bunch of round trips when you're doing your SSL handshake. Use wildcard certs if possible. That way your cert will match multiple domains, and so you can do connection pooling and Speedy, which can end up being a significant latency reduction. Use reasonable SSL write buffer sizes. Try and use server push instead of inlining. Inlining we'll talk about in a second if we have time. Use appropriate selection of priority. For instance, HTML is most important, and JavaScript and CSS is pretty darn important, and the rest of it is probably not anywhere near as important. Pick an appropriate frame size so that you can do interleaving with reasonable latency. Our implementations use a 4K frame size, which seems to be just fine. It doesn't add too much overhead. Leverage persistent settings. So one of the things we didn't talk about very much earlier is the fact that Speedy allows us to have some settings about your TCP connection saved on the client machine. And they are connection settings like measured RTT and measured CWIND. And what this allows you to do is this allows you to very quickly resume the CWIND that you had with your previous session on a future session. Another thing that you should do is turn off TCP slow start after idle, which is frankly kind of evil. Set init CWIN to 10, and that's basically becoming a standard as far as I understand, so you should probably do it anyway. And whenever possible, use a single connection, because otherwise you're contributing to various problems on the internet. So server push versus inlining. Please remember to mute. Server push versus inlining. Why do people do inlining? Well, first of all, people do inlining because they need to reduce the number of round trips total. Makes sense, right? So what they do is they encode the data in the web page itself in a base64 format. Hopefully they get to compress that page so it doesn't blow up too much, but there it is. Now the biggest disadvantage there is it will never be in the cache addressable as its object. So that can be a problem for future page loads. So people tend to, it's very difficult because sometimes people don't do it multiple times, and sometimes they do it. So another interesting thing about server push is because we don't have to re-encode anything, you are never increasing the size of the resource. Right? So we're hoping to get people to use server push. We note that it may have more interesting, and again, people on the VC mute. There are people who are not muted. Make sure you are muted. Thank you.
Raman at Google, you need to mute.
Oops, sorry.
All right. Another thing that we're doing is researching TCP level improvements. We hope that this will have an impact on things that are not just speedy, but we definitely know that there are things that it will help for with speedy. In particular, we know that there are some instances where speedy doesn't perform as well as HTTP on high latency, high loss links. This is due to the fact that the amount of loss for a speedy connection is more. What I mean by that is the amount of loss of bandwidth for any particular packet loss is more. And we need to fix that because we should not be incenting people to use many connections. Standardization, this is a big one. We're going to IETF in spring. So we're beginning the standards process. We've done our experimentation. We believe it works. We believe it actually makes sense to make this a standard. We're going to IETF with it, and thankfully there will be other contributors there externally to Google, Mozilla, for instance, who will be there with us. Areas for research.
Maybe we should go to Q&A.
All right. Okay. Questions? Yes.
One?
You said you had, so the better performance with the packet loss you think is due to TCP fast recovery kicking in better than single connection?
No, the question was about better performance in terms of packet loss. So basically, when you have multiple connections, you have multiple C-wins. So when you have a single connection, when you have a packet loss, the C-win drops in half, right? If you have 6 connections, now only one of them gets dropped in half. So that's effectively a 1/12 loss in bandwidth as opposed to 50% loss in bandwidth.
Right. And in cases where there isn't quite so much packet loss, yes, speedy can actually do better, which was, I'm not sure which sense your question was, but it can do better exactly because, as you suggested, it triggers the fast retransmit path because there's more likely to be a subsequent packet on the same connection.
Right, that's kind of Mark. Your previous graphs where you showed speedy
Yes.
better with packet loss. That's kind of
Yes, it depends on how much packet loss you have and what the latency is.
Do you have a sense where the 15% improvement comes from? Which aspect of speedy gives you that 15% improvement?
Honestly, we don't have a great sense, and the main reason for that is that it's changing all the time. So even if we analyzed it then, I can tell you that the results today are very likely different, but we are going to be presenting some interesting numbers about what happened with Websearch at the very least at Velocity very soon. So the question was, is speedy a drop-in replacement on server side? So long as whatever the server framework is speaks the speedy protocol, the answer should be yes. But that is for current web pages. If you want to do something speedy specific, obviously you need to do something speedy specific. So the question was, is there a transition path for, I guess, application writers so that they can see when the client is coming to them via speedy and react to it? I would imagine that'll depend on the exact server implementation. I can say at least for Google servers, what we do is we will simply advertise that the connection came in via speedy, and so they can react appropriately.
So just to be clear, the server will know whether or not it's over speedy over normal versus normal HTTPS because that information is in the TLS extension next protocol negotiation. So servers always have that information.
What do you expect the role of the proxies to be in the future? Basically killing all proxies?
So the question is, what do we expect the role of proxies to be in the future, and is this killing all proxies? So no, it isn't killing all proxies. But at least my hope, and since we're going to standardization, we will not be the only ones saying anything about this. But my hope is that it will change us to a world whereby the only proxies are authorized proxies. So they are the ones that you agree to use, as opposed to today where we have these transparent proxies that you don't agree to use. They may do things you don't want them to, and you have no control over it. Does that answer your question?
Sure. I'm curious what you think of authorized proxies.
It would be one that you've configured in your browser. The question was, what is an authorized proxy? The answer is, it's one you've configured to be.
So today in Chrome, you can configure a Speedy proxy, so you can talk directly to a proxy with Speedy.
Right. Any other questions? So the question is, you mentioned some concern over high loss, high latency links, and the question is that where the mobile web is going? I don't know. As I said before, we need to gather some more numbers on the mobile web. Now, the interesting thing there is that it may very well be that bandwidth isn't the dominating factor in many cases, or at least the recovery is fast enough that you can deal with it. It may not be. I don't know yet. We are running a battery of experimentations, of experiments to try and see what we can gather right now, but we're also going to do some real-world tests as soon as more browsers are available on the mobile handsets and devices, that can actually speak Speedy.
Without giving away any numbers, internally at Google, we have run some lab tests, and it shows that most of the costs in those high latency, high packet loss connections is because of CWIN getting throttled. So multiple connections does win out in that case, and for now. And that's why we're looking at trying to improve the state of TCP implementations at Google and also out in the wild.
Question about Android. You mentioned it's Speedy is supported in Android. So am I getting Speedy when I go to https google.com?
It depends on what version of Android you're using. The Android browser in Honeycomb and in we can't say anything else. But if you write an Android application, no, that is unless it's using WebView, it is not going to be able to speak Speedy. Yeah.
What about ICS?
I can't say.
Okay.
Any other questions? All right, how much time do we have left?
I think we're
1 minute.
Should we go?
Yeah, so since there are no other questions at the moment, we'll talk about the other two things that we didn't mention before. So we'd like to allow the server to authenticate for other host names. So right now, when you make an SSL connection, a cert is served. That is the only cert that is served over the SSL connection normally, unless you renegotiate. But without going through the pains of renegotiation, what we should allow is for the server to announce that it has this other cert, and thus it should be able to authenticate that it is actually valid to push down requests for this different host name down the same connection. And this, because it's a cert, will hopefully be at least as secure as any other cert-based authentication mechanism can be. Another thing that we would like to research is possibly pushing or republishing DNS data down the same pipe so that you don't have to do additional DNS queries in order to figure out that you should use the same connection or maybe use a different connection. There's another aspect to this which is also interesting, which is that if the server can publish DNS information for its own host name, it can actually steer traffic to a different IP for the same host name. That's actually really interesting for load balancing, and potentially it would actually end up with reduction of latency, because right now most localization for domain names is done, unsurprisingly, by your local resolver. And unfortunately, your local resolver may not actually be local. We've seen cases where, for instance, people in Africa have a domain name server in Europe, and I promise you that if that domain name server is handing out things that are close to Europe, they are not close to Africa. So a mechanism like this would allow the server to realize that a problem had happened in the DNS resolution, or at least a suboptimality, and to fix that. And I believe that's it. Do you have any more comments?
I think we're out of time.
Yeah, so we're out of time. Thank you for allowing us to present.